Okay, hello. I think I might be live streaming. I don't think there's anyone here yet, but let's see. Okay. Welcome, Sanket. By the way, we are live.
Okay.
How are you? Welcome, everyone who happens to be viewing. I see that there are 4 viewers. They're probably all Cosmology from Home people. Um, we made it. Can someone please?
Say something. Can you hear us?
Yeah, I can hear you, and we are streaming. Can someone please copy this to like the previous video so that if anyone happens to be checking that out, they can see that we are here. And as I
Maybe
said,
we should
we
also
are
update
currently
the
live.
Reddit on
I don't
Reddit.
know. Yeah, maybe. I don't know if we can do that. Actually, that goes to a Cosmology from Home webpage, so we could edit that. Ben, if you're watching, go to cosmologyfromhome.com and set up the redirect to this link. Anyway, welcome to Cosmology from Home's live stream. As you can see, we had some some minor issues trying to use software that's more complicated than we wanted. But we're here now. So as that I can take a short break to recover, does somebody want to put up their hand and tell us about something interesting that they learned at Cosmology from Home this year? Nico, thank you. You
Sorry, I'm
appear.
trying to.
Oh, yeah.
Yeah,
You
can
were
you hear
pretending to be
me?
muted.
No, no.
Not
Hi,
fair.
everyone. So, what I learned, I think the most important thing that I learned is, well, apart from meeting new people, is just like what is currently trending in cosmology research from both theoretical, observational side. So, just bits and pieces from, like everyone's work. I particularly liked some of the discussions we had on the blinding strategies in cosmology. That was really, I found it very important for my work personally, but also filling in some gaps in knowledge that I had. And then also some updates that we have in the realm of large language models and how AI is helping science in general.
Cool. Okay, I think I'm a bit more energetic now. So let's actually go through and I'll change the gallery view and we will introduce ourselves. And this time, dear viewers, you will actually hear us. So I am Sean. You might recognize me as the owner of this channel. And I used to be an active cosmology researcher, mostly on kind of early universe, but I found that as I worked, I moved forward with the universe. I moved at much faster rate because in uh, about 10 years of career, I worked from the very early universe to the current universe. So I did 13 billion years in 10 years. But now I do stuff like this and normally a lot better than this. But next on my picture is, I guess, Sanket. Do you want to introduce yourself?
Hi everyone, myself Sanket Dave. I'm an MSc graduate from University of Sussex, and yeah, I'd love to interact with all of you.
Cool, thanks. Andrea.
Sure. Andrea Fiorilli, PhD student at the Max Planck Institute for Extraterrestrial Physics in Munich, Germany. And thanks a lot, Sean, for keeping this running and organizing all of this.
No worries. Priel.
Hi everyone, I'm Priya Bodia and I am doing my master's in theoretical physics at University of Bologna.
Wonderful. And Nico, sorry, Sergio, sorry.
Hello, everyone. My name is Sergio, and I'm a postdoctoral researcher in Institute of Particle Phenomenology at Durham University, and I do cosmology and particle physics all together.
Excellent. And Swagat?
Hi there. My name is Swagat. I'm a research fellow at University of Nottingham. I work on early universe physics and cosmology, and it's a real pleasure to be here on Science Talks channel, which is really great.
Awesome. Now, Nico.
Hi, everyone. My name is Nico, and I'm a postdoc at Duke University here in the US. And I'm very, very excited to be here again.
Cool. And Daniela.
Hi, Sean. Thank you very much for organizing this. I'm Daniele, and I work as a researcher at Durham University in the UK. I work on cosmology and galaxy formation, mainly theory and numerical simulations.
Great. So, if you've just joined us, Nico was telling us about things she learned at the conference. And one thing she mentioned is blinding. So let me just change back to speaker view. What is it about blinding that is so important and interesting to science, but I guess especially cosmology?
Are you asking me, right?
Yes.
Right. So just to define what we mean by blinding. So what most people know about are, for example, these special ways of doing research from from medical science. This is basically where they do clinical trials. So what they do is that they're testing a new drug. They will have the new drug, but also they will have the placebo pills, right? So we will distribute these pills, both the new ones and the placebo, toward the people who are being tested on, and then that's how they're making sure that the pill actually works. So we have some sort of equivalent like that in physics in general. So it can be particle physics or cosmology. Now, because the way that the science is done in these two different fields, I'm just mentioning. Sorry, my phone is ringing. The way we go conduct science in particle physics is very different from the way it's done in cosmology. We have to have different strategies, and why do we do that? So it's basically trying to conceal the data in a way. So we process data using pipelines, and we have to be confident in our modeling or in our analysis choices, for example. But there is a factor that it is impossible to remove, and that's the human factor. So what you can do is bias yourself. So for example, if me, Nico, for example, I really like the cosmological framework we call lambda CDM, there is subconscious way for me to convince myself that what I'm seeing from the results is actually that, whereas the truth is not lambda CDM. So in order to do that, we have certain strategies to help us not bias ourselves from later on reporting on the results. I hope I kind of explained it well. Maybe somebody wants to chip in on that. So please go ahead. Maybe Sean, you want to say something?
Yeah. I think you expressed it quite well. But one of the natural thoughts I think someone might have when they hear that is like, well, what if I just try really hard not to be biased? And in a sense, yeah, that would work, but it would work too well. And if you knew that, oh, I like lambda CDM, so okay, I like lambda CDM and I don't want to be biased towards lambda CDM, I'm going to be so careful. I'm going to make sure I'm not biased to lambda CDM. Guess what you've just done? You've now biased yourself against lambda CDM. So now all your results are going to have that bias. So how do you know where the neutral value is, where you're unbiasing yourself just enough that you're not now biasing yourself in the other direction? And that's very hard as a finite human being. But if you blind all your data, then any like internal preferences that you're trying hard not to take into account, but not trying too hard not to take into account, you just don't have to worry about that anymore because you don't know the answer. So whatever effects you're playing with, you can't emotionally be attached to them because you don't know what they're doing. Cool. Does anyone else want to jump in with that original question of what did you learn from the conference?
it might be too fresh for people to to answer, right?
Yeah, maybe. What is on your mind? Sanket. Yep.
Yeah, like one very important thing I would say is that in this conference you do get to learn about and like various different things, even if you're not an expert in those topics. What happens in usual offline conferences is that we normally attend to conferences where we know some things about. So in this conference, I mean, so we got to learn about the very recent results of SPT, and we got to discuss directly with the experts involved in those particular results and so on. So it does give you a very nice opportunity to interact directly with people directly involved in these very big surveys and so on. Even if you are not an expert in that field, it allows you to really participate really nicely and so on.
Cool. I think Sergio wanted to answer the following question. So just for those of you who aren't aware, we're also doing a Reddit AMA. Maybe one of my co-streamers can put a link to that in the stream chat. And one of the questions asked there was, what single measurement do you think would be most useful towards clarifying existing tensions, but which has not been made for technical or budgetary reasons? In other words, if you could have a wand and have one number measured by a current or next generation experiment, what would it be? So just before you answer, Sergio, I'll give a quick context about what these tensions are. So in cosmology, there's a lot of different telescopes measuring different things. And sometimes we get this situation where one telescope, one way of measuring something about the universe is telling us one answer and another one's telling another. So the famous one at the moment is the Hubble tension, where if you measure the cosmic microwave background, which is light traveling from very, very early in the universe, and try to work out how fast the universe is expanding now based on the temperature that it arrived at us and various other things about it, you get one value, but if you actually kind of locally measure it with local stars and supernovae, you get another value. So both of these things kind of are consistent on their own, but when you combine them, there's a tension there, and there's a few other things like that going on. So with that context, Sergio, do you want to what would be your your dream experiment?
So yeah, I think that the obvious answer would be the Hubble tension, like measuring H naught. But I wouldn't choose that because I think that if we knew H naught, we wouldn't actually learn that much about our universe. Say that we have some value. It's true that maybe we would know if Hughes measurement, like the local measurement from the distant ladder, is the correct one, or Planck measurement is the correct one. We could know more or less how to solve the Hubble tension, but I mean, in a way, we wouldn't be looking at kind of like the real problem, or at least finding a solution. So I think that for me, the one that I would choose is omega naught of if there is a dark energy field, it will have some type of cosmological constant behavior, or maybe it would behave as a dynamical quantity. It would be like a quintessence field, for example. So we know that if this field is changing with time, it could take different values for its equation of state. So the way it impacts the expansion of the universe. If the equation of state is equal to -1, it's just a quantity. If it's equal to -1, it basically means that its pressure is the opposite to its density. So it's always kind of, it will behave as a cosmological constant. It's always able to give more and more and more expansion to the universe. If the equation of state is equal to 0, then it will behave as matter. And if it's equal to a third, then it will behave as radiation. So the thing is that we have different experiments right now, or observations, that, well, we know that lambda CTM expects this number to be -1. But for example, recently DESI found that this value has, well, they find that it has to be changing, or it could be changing. And if it has to be changing, it will behave in very weird ways. It would kind of behave in, well, today would be like, would have a value that is slightly bigger than -1, but in the past it could be even smaller than -1. So I think that knowing this number, exactly what is this omega naught, could tell us a lot about whether DESI is right or not, and not only that, but also the Hubble tension, whether it's right or not. And it would not only kind of point to what type of problem is the correct one, but also to a solution. We will know that there is quintessence in our universe, or there is no quintessence in our universe, and we could move on to a different type of late time cosmology.
Cool. Thanks, Sergio. I don't see from our group of panelists anyone wanting to follow up on that. Maybe Nico.
Oh
Yep. You
yeah,
want to follow up?
yes, yes, yes. Thank you, Sergio. And I agree with you. My answer would be much less fun. It's more boring answer, but the measurement, a single measurement, I wouldn't call it a single measurement. I think what I would really like, and I'm sure that everyone would agree, actually, is the measurement of redshifts. So believe it or not, the distance to objects is super difficult to measure. Of course, here we can measure the distance to the moon very, very confidently and precisely, however, and accurately. But distances to very distant objects like galaxies are extremely difficult to measure. And the measure of distance propagates into every other measurement that we do. So for example, no matter what kind of probe you do, so that means how you are studying the universe, for example, the way Sergio is doing it from a theoretical point of view, and also doing talking about the dark energy or dark matter, or the what he mentioned, the H naught, so the Hubble parameter measuring the value of parameter, they all depend on the measurement of distance. So if we could improve our experiments, meaning having even better telescopes or finding very clever ways to clean up our signal and to model these distances, then we would be in a much better position of understanding the universe.
Cool. Thanks, Nico. We've had a few questions coming in actually from the stream. So I'm going to go to Leif's question. What's the status of the S8 tension? Have any recent results relaxed that? I can't help but wonder whether you, Leif, know the answer to this question, because that's far too on the nose of a question. Does anyone want to tell the stream what Leif, I think, wants us to tell the stream? Okay, I'll have a go. The S8 tension, for those who aren't aware, is or was, which I guess is spilling the punchline before I get started, but was a tension, one of these tensions I mentioned earlier between different measurements. But again, it was kind of between measuring the cosmic microwave background, and then by looking at that and inferring what the current universe should be like, you kind of predicted that the fluctuations in the density of the universe should have a certain amplitude. As you move around the universe, the density should be changing by a certain amount. But then when you went out and measured that using primarily the best measure at the moment is something called cosmic shear. You see how that matter is lensing distant galaxies. That appeared to be getting a value that was, if I remember correctly, lower than what you would infer from the cosmic microwave background. However, in the kind of last 2 or 3 years, as techniques got refined, it's gradually become the case that those two ways of measuring this S8 parameter, or the average fluctuations in the density of the universe, have converged more or less to a similar value. So yeah, the status of the S8 tension is that at least the kilodegree survey, the dark energy survey, and the hyper supreme cam appear to have converged to the cosmic microwave background. However, even now, there's still perhaps things like galaxy clusters might appear they're not as many as you might expect and stuff like that. And when there was the story that you had cosmic shear and galaxy clusters and a few other things all kind of pointing in the same direction, it was very interesting. Now that cosmic shear is kind of merged with the early universe prediction, the galaxy clusters are kind of sitting there on their own. Does anybody want to follow up on that before we tackle another question?
Perhaps just there are explanations of this S8 tension and the latest tensions in cosmology. It might be a bit technical, but maybe not too much. You can look up Cosmoverse paper that was put out this year. And
also, I think the most recent video on this channel by the kilodegree survey would probably be my go-to resource on this. And so that's partially why I thought Leif might know the answer, because if you go to the videos on the channel and see the thumbnail picture will say no S8 tension. Right, let's move to the next question by Yellow Gorse. Thank you, Yellow Gorse. Is it true that there may be as many rogue planets as planets orbiting stars? I have absolutely no idea. One of the funny things about being a cosmologist is that people think you know about astronomy, and I'm sure there's someone in the audience in the panel who will know the answer to this question. But yeah, like it can be funny how little cosmologists know about astronomy. I'm not even sure I know the difference between what a rogue planet is and a planet is. But does someone want to tackle this? First of all, when answering, for those of us who are lay people on this topic, tell us what a rogue planet is and what a planet is. I will remind my panel to raise hands when they want to answer a question. Maybe we're all ignorant. Andrea, you can have a go.
No, I totally second what you said about being a cosmologist. I also have no idea what the actual answer to the question could be. Just maybe clarifying to the audience, a rogue planet is a planet that doesn't orbit any stars. So it's just free floating, going its own way through space, pretty uninhabitable space as such. I have no idea, although one thing that we're quite sure about is that planets should form more or less in the same places as stars, in the sense that you will have these clumps of gas inside galaxies that get clumped together more and more by just gravitational attraction, by just the fact that there is an overdensity of gas at a certain place. And if they have a way not to become too hot, which would counter the gravitational attraction and disperse them by radiation pressure, if they have an efficient way of cooling, people that know astronomy would actually know what these ways are, but I'm gonna jump over it. And they will form denser and denser clumps that will eventually become stars, and material around stars that will potentially form planets. So I would naively expect planets to be more or less in the same place as stars, but then you can have all sorts of complications. Of course, they can have you can have turbulent dynamics inside these clouds, and they can get kicked somewhere. One thing that is probably worth mentioning is what would be a very cool way of detecting rogue planets, and that would be microlensing. Now, microlensing is kind of a complication of another effect which we observe, which is strong lensing. Strong lensing is when we have a source of light that we can observe, and something massive passes in front of it, like, say, another star. So what will happen by the theory of general relativity is that the light of the background object will get slightly deflected towards the object that is passing in front. And so we will see a total flux of light, which is more than the sum of the two, background and object passing by, because we get more light from the background object, which is deflected. Now, this is the strong lensing. The microlensing is something even cooler. Say that within the span of this event, you have a planet orbiting, or you have something else passing by, like a rogue planet that just happens to be in line with what you're seeing. That will add another small top excess of light about what you're seeing. So you will kind of have a lensing on top of the lensing. This is a very cool way of detecting, well, not only rogue planets, but planets in general, right? There are exoplanets that are orbiting stars that have been detected through this way. And I find it super cool, although I'm totally not an expert in the topic. I think Swagat wants to add something.
Yep, go on, Swagat.
Yes, so I'm not an expert on many-body dynamics, but one of the ways you can get rogue planets is when you have multi-star interaction, and this can happen in dense stellar environments like a stellar cluster. So typically when you have many-body interaction, often one of the objects, like let's say a planet, can get a kick, and then that may become a rogue planet eventually. So in that way, there could be many rogue planets which are formed by just purely gravitational interaction of many stars in a dense stellar environment. But I do not know the answer to whether the number of planets around us bound to stars are more or less than the number of rogue planets.
Cool, thanks. So the next question I see in the chat was, can gravitational waves give us a more reliable way to measure the universe's expansion? Will they help settle the Hubble tension once and for all? Yeah, Swagat, you want to tackle that?
Yes, I have some thoughts on this topic, so I would like to share with people here on YouTube. So we have currently two different measurements. One is based on early universe physics, and that is the cosmic microwave background measurement, and it measures the present rate of expansion of space, known as Hubble constant, to be a particular value, and it's in the ballpark of around 66 to 68. And with a very small error bar. So the 66 to 68 that I quoted is too broad. So the actual measurement is much more precise than that. While there are direct distance measurement techniques based on, let's say, to give an example, based on supernova observation, and they measure Hubble present rate of expansion to be faster or higher, and it's around in the ballpark of 73. And so there is a disparity between them, and they both are precise enough so that they don't overlap at more than 4 sigma level. So the question is, if we have a third and independent way, would it solve the Hubble tension? If the independent way has less systematics in the language of cosmology, in the sense you understand the physics very well to determine Hubble parameter, and its statistical fluctuations are also small, and then if you measure it, yes, definitely it can point us towards which of the Hubble is more reliable, the late universe or the early universe. It will still not answer what was wrong with the later or the early universe. Okay. Now said so, the proposal was that gravitational waves coming from colliding neutron stars would be a way to do it. Nico pointed us out that one of the most fundamental measurements you should do are redshifts and distances, right? When we measure gravitational waves from merging black holes or merging neutron stars, from looking at the wave, the detected gravitational wave, we have a good understanding of the distance from which the wave is coming. However, if these are neutron stars colliding, then they also emit electromagnetic waves, and by measuring electromagnetic waves, you can also know their redshift. So it's a good probe of knowing distance and redshift. So we were very hopeful that we can measure many such events and then solve or address the Hubble tension. Unfortunately, in the last 9 years of observation of gravitational waves, we have only seen 2 neutron star collision events, and only one of them had a redshift data. So it looks like such events are rarer than we thought before. So they are not being very helpful in decreasing the statistical error on the Hubble value. So people have come up with novel techniques in that using black hole collisions to get the distance, and then realizing where the black hole is located with respect to a known galaxy whose redshift you already know. From there, you can know both distance and redshift. But there are huge nuisances or intricacies in this cross-correlated determination, and so we are not sure. So the answer is it looks promising in principle, but in practice, it requires a lot of statistical error being reduced as well as systematic error being reduced.
Cool. I think Andrea has a follow-up thought or even a question for you, Swagat. We'll start questioning each other.
Yeah, no. It's just because I don't know the progress in this specific field, but this thing that Swagat explained of the binary neutron star emerges that came to be known as multi-messenger astronomy. Multi-messenger being electromagnetic waves and gravitational waves, the two messengers, used to be a big thing in the late 10s when I was starting university. That was like a very, very promising field. And then, as you explained, the hype is going to be down nowadays because we only saw 2 multi-messenger events. How did this back react in the models that we have about how compact objects are formed and how they behave dynamically with respect to each other? I hope this is not too technical, but I think like should be fine.
Yeah, before I let it go back to Swagat, I will warn my panelists to not turn this into a cosmology from home discussion at the actual conference. Although I think kind of in some sense that would be nice because one of the things I like about the conference at a more technical level though is that when you see the experts on something that you're kind of not an expert on discussing and actually asking each other the questions they want to ask each other. I really like that because then I, as a kind of outsider to that sub-cosmology field, can actually work out and know what they find interesting. So I am going to let this conversation go. But I'm just going to ask my panelists that when talking to each other about these kind of slightly more technical things, to do it as much as possible in language that will be more generally understandable. But I think I hope the audience actually finds this very interesting. And of course, we're on Cosmology Talks channel, where most of the stuff on this channel is aimed at researchers anyway. So please,
if I can try and
Swagat
phrase
can,
it in a, if I can try
Yeah.
and phrase it in a more down to earth way, like
no, well, let's maybe just. I think you did a good job. So
on you go.
Swagat, if you can respond relatively briefly, then we can. Lots of people have ticks waiting to have thoughts.
Thank you, Sean and Andrea. So the question is about, we had a pre-expectation of number of neutron star events that we would have seen before 2015, before we observed any gravitational waves. And after observing, we have figured out that our expectation was too high. And so we have revised our sort of understanding of how many neutron star binaries are colliding in the universe to make it short. And we think it is much less than we thought a decade back.
Sorry about that. I was renaming my name because I noticed that I'm Cosmology from home in the stream, not my actual name. Daniela, I think you're next to respond.
Yeah, so I wanted to go back to what Swagat was saying, and I totally agree that the key is having, other means of measuring distances independently, but then all the complications that Swagat has explained have come up. So just to bring it back to the original question, Swagat, would you so the question was posed, I believe, by saying, will that help settle the Hubble tension once and for all? So would you say that the answer is no, or not anytime soon? Like, what would you bet will happen? Does this have good potential in the future? Because it doesn't seem to have that right now.
Yes, so I'll briefly say that it's a combination of three answers, not three independent answers, but three combinations. Answer is not anytime soon, for sure. Second, we need to have all the systematics in control. So we don't know whether we can. In the sense, we need to understand the physics of how black holes collide and which galaxy they are located in. Third, and more importantly, even if we have a third measurement very nicely done, it points us towards one or the other, we still don't know what was wrong with our original two measurements. So either of them. So it's not a straightforward answer at all. It will help definitely, but it may not do it once and for all. We need to do extra.
Okay, Nico, you have a thought.
Yeah, I just wanted to wrap it up by saying that, Andrea, I think you're biased because you now are in a very niche field working on a thing, but actually there's a lot of science being done regarding rotational waves and multi-messenger astronomy and astrophysics or particle physics or astroparticle physics, however you want to call it. So I don't want to single out one person, but I would say I think that Sean, you hosted at some point, Tessa Baker is a very good lecturer, and there should be some videos on YouTube about that. But they are putting everything in a catalog. It is being processed, and they're waiting. That they already have some very good conclusions. What's going on is just that these events are like you have to wait for them. But people are working on it actively, and also the rotational wave lensing. That's a thing. I actually went to Manchester last year to listen about that. So things are being worked on a lot. It's just that we kind of are in different fields, so we forget about it. But yeah, it's gonna be great. Like I really enjoyed learning about how they're doing things, and I agree with Swagat completely.
Awesome. Thanks, Nico. One of the things I quite like about Cosmology from Home, speaking as a Cosmology from Home organizer, is that we set aside time for talks about academic life and public engagement and things like that. One of the really cool things we had this year was a plenary talk at the conference about this program called the Supernova program, which is a mentoring program for women in the industry. And really nice that we have Priyal with us in the stream, who's one of the key members of that organization at the moment. So if Priyal wants to, I would love for her to be able to, because I don't know who's watching the stream. There may be some young students who are interested in some mentoring, and they might very much like to hear about the Supernova program. So Priyal, if you want to tell us about that, that would be awesome.
Yeah, thank you, Sean. Yeah, definitely. I would love to share about Supernova Foundation. So I will just start by talking a bit about the organization. So Supernova Foundation is basically a mentoring program and a network of women physicists from across the world, where more experienced
Priyal, I think you might have a non-ideal connection. Is it possible for you to turn off like the video that you're watching of us, and then it might be a bit clearer?
Maybe not.
Yeah. Yeah, try again. Yep.
Okay. Sorry, I'm just closing the other windows so it doesn't get in between. So yeah, I was saying that Supernova Foundation is a network of women physicists from across the world, and it's basically a mentoring program where more senior researchers and physicists they mentor younger researchers and physicists, and this can range from undergraduate to PhDs, and there's also a lot of peer mentoring between more senior researchers. So yeah, there's like a lot of amazing things happening. Like we have some webinars, which is between the people in the organization, and there we talk about how like things that we don't usually learn at university level, like creating a CV or how to progress with your application process, because I mean we all have had so many of them throughout our careers. So yeah, and also that organization has had amazing they have been able to create some amazing connections, like we talked about in our talk that you can find soon on the YouTube when it's made public, that there have been two mentees who ended up being roommates in one of the countries, and there have been a lot of mentors who meet at different conferences where they might have been like the only women at some point. So that organization has been doing some great work.
Cool, thanks. So Nico is very, very keen to answer one of the questions from the Reddit AMA, which was about how the Rubin Observatory will help us. And I know that Nico works on data that will be coming from Rubin. So Nico, do you want to
Yes,
tell us
of
about
course,
that?
I had to answer that question. I was saving it for the live stream. I know it was already answered in partial way, Ben. But P Healthy on Reddit, thank you very much for your question. So I'm sure that most of you, if not everyone, watched the first look from the Rubin Observatory that happened on Monday. And we at Cosmology from Home also watched it. We had a watch party. And here at Duke University, we actually watched it from the stadium, which was fantastic. And so the question, how will Rubin help us advance cosmology? Well, first and foremost, it's a fantastic instrument. It is absolutely incredible. So you can look up the specs, and I think you can, if you didn't watch the live stream, you can go back and find it on YouTube or on the website of the Rubin Observatory to see the specs of the instrument. But I can just say that it's absolutely brilliant. And what we are interested in is how much sky you can cover. We call it the footprint of the survey. And because of the location, this is a ground-based telescope, right? It's in Chile, so because it's in the southern hemisphere, it will cover during the 10 years of service around 40% of the sky. So quite a bit, basically almost half of the sky, which is fantastic. And not only that it's just going to cover a lot of area, but also the resolution of the images is brilliant. In order for you to maybe, for most people to understand, just think about your phones, your cell phones from 15 years ago, and how the cameras, like the photos, looked before, and how the technology progresses. For example, on your iPhone, right, we have all these fancy cameras. So now the photos are absolutely mind-blowing. And this is made right for mass. This is mass product. The telescopes, or all the cameras that we have, are specially custom made for science. So it's like extra super cool. And this is what makes it, right, so much better than the instruments we had before. Maybe if you can compare the images from what Rubin showed us on Monday, and you can see this is from it's, as I said, it's a ground-based telescope. So it is a telescope that, when we're observing, we have the atmosphere to fight with and all other stuff. And the quality of images are still so much better than what we we could have done 20 something, 30 years ago. For example, Hubble's Space Telescope, which is one of the best things humans ever made. But you can see how technology improved, because I think that the Rubin images now are better from the ground than what we had from Hubble. So how are you going to, why this matters? Well, it helps us resolve, right? Because the resolution is so much better, it helps us resolve different galaxies. We can probe further into the past. I think that Rubin is going to go up to redshift 3, 3.5, 4 even. So that's fantastic. And also it will be able to see very, very faint galaxies. And this is what we need. We need to cover a lot of sky, so we can have a big chunk of the universe to observe, right? With the way Earth is moving around. And then also, excuse me, to see as many galaxies as possible, and faint ones are also the key. We really want those really faint galaxies that are really far away. So it will give us much more data. So one of the key things is more data, right? We're going to be able to see more galaxies with very, very nice resolution. So then it is very important to have we call it good statistics, right? That just means a lot of galaxies, much more than previous surveys, and also with higher resolution. And that will help us in cosmology to crunch numbers better. Basically, it will just give you a possibility to crunch numbers better. But everyone is studying universe from different perspective. For example, I think Ben mentioned on Reddit, rightfully so, that people who work on supernova and these transients also are going to have a lot of beautiful new data with really, really nice resolution to study and to probe. So in that sort of sense, however, of course, no instrument is perfect. So you have to always have trade-offs. So another thing that is that we in cosmology are very excited about is combining data from different experiments or different telescopes. For example, NASA's Roman telescope, which is going to be launched in space next year, is also going to be working together with LSST. We're going to have synergies between these two surveys, and that's going to be super exciting because they're very cool. It's basically like, think about NASA Roman Space Telescope as a new Hubble that's going to be in space. So it's going to be like even super cool. And then combined with Rubin, it's just going to be really lovely to work on. Sorry that I took on so much time, but I'm very, very proud and honored to be working on LSST and Roman.
Yeah, it'll be very exciting to see in the coming years all of the results, and hopefully many talks on cosmology talks about the results as they come out. We had a question in the chat from Taylor Benji. Is there any way to infer the topology and potential extrinsic curvature of the universe? After all, GR, general relativity, only describes intrinsic curvature. So let me maybe unpack that question for people who don't know the technical terms there. So intrinsic versus extrinsic curvature is this idea that a space can have kind of a curvature, that if you move through it, you're not traveling in, even if you travel in straight lines, this whole idea of like parallel lines can converge if something's curved. The kind of textbook example of a curved space is a sphere that even if you start on two hemispheres and go in a straight line on the surface of the sphere, you can kind of meet. There's no way of taking a sphere and making it a flat thing. So extrinsic and intrinsic curvature. The intrinsic curvature is something that's intrinsic to the actual space. It doesn't have to be embedded in a higher dimension. You can actually just be staying in, say, if it's a sheet of paper, a two-dimensional space, and still be finding that you're curving. Or you can scrumple up that bit of paper and then now it's got curvature in that third dimension. So if I understand the question correctly, the idea is that general relativity is describing 3 dimensions of space and 1 of time, and it describes intrinsic curvature in that 4-dimensional, 3 space, 1 time space. But of course, in principle, there could be additional spatial dimensions. So I think the idea is that maybe there's some sort of extrinsic curvature as we sort of leak into this 4th spatial dimension that may or may not exist. I'm not saying that it does exist, but in the questions universe, it does exist. Is there any way to kind of measure that? And then topology here is kind of describing how to describe topology on a lay level. It's like the kind of big picture structure of a space. So for example, if you've got, say, something like this coffee mug, the big picture version of this is that you've got a kind of thing here and then a hole here. And you could completely deform this coffee cup, but so long as it keeps this hole, then that is the topology. This is essentially a ring, right? Like I could squash my coffee cup into just this bit here, and you would have a ring. So topologically, my coffee cup and a ring are exactly the same thing. So the universe might have some sort of complicated topology. As far as we know, it's just completely flat. It's not a ring. It's just a boring thing. But it might have some sort of ring-like structure. If you go far enough in one direction, maybe you come around and come back in the other direction. So I can maybe have a go at answering that question now that I've explained the question to the audience. But do any of my panelists want to have a go at talking about how we might infer the topology and potential extrinsic curvature of the universe? I don't see any
Sean,
enthusiastic hands. Yep, sorry.
I can say, but if you want to answer first, go ahead, and then I can
I
add
was
to it if
hoping that I
have
might
to.
have a bit of a think about the answer while someone else was answering,
I
because I was
see.
only thinking about how to explain the question.
Yes. So maybe I can say a little bit because I'm not an expert on this, but this is a really active area of cosmic microwave background research. And in the institute where I did my PhD, one of the leaders of CMB in that institute was leading this effort of looking into detecting non-trivial topologies of the universe in the cosmic microwave background data. So I'm saying everything that I heard from those days. And it's still ongoing, by the way. Yes, so everything that we observe, including a flat geometry, a flat space, 3-dimensional, is consistent with being a flat and a ring, like a torus. That's also possible. So a flat 3-dimensional space could be either infinitely big, or it can turn back on itself in some non-trivial way, basically. And the question is about how do we know, for example. Okay. One of the ways you can think about it is that if it's like really a torus, turns back on itself, then and if its length is not too large, okay, so we have an observable universe of some size, and if it turns back right outside the observable universe, then you can see multiple patches of the same sky again and again, because light can just traverse through it. Okay, so if you look at cosmic microwave background, there may be effects of multiple images of same type at slightly different patches of the sky. And this would typically appear on larger length scales. So you have to look at the temperature fluctuation pattern in this cosmic microwave background at 2 angles which are very large. Okay, this is almost like 30-degree, 40-degree separated. Unfortunately, for very large angles, our statistics is low because we can only have few patches of sky. So currently, all searches for detecting such kind of non-trivial topology have not yielded any conclusive answer for us. Okay. Other reason could be that if at all the topology is non-trivial, it is so large or so big that it will have no observable effect for the next many decades of improved experiments. So we have to be lucky to detect a signal like that.
Thank you. So I think we've got someone in the panel who will like to have a tackle of Chavis von Bradford's question. So let me ask the question and then try and decipher it again. So do you think we will make a breakthrough on the phenomena of the grand unification epoch with experiments and observations? So the grand unification epoch, to explain it to the audience who may not know what that means, in physics, so not cosmology actually at the moment, you have various forces. There's like the electroweak force that's responsible for example, how atoms decay, the strong nuclear force, which is, I guess, responsible for how atoms don't decay, for holding the nucleus together, the electromagnetic force. As you change the kind of energy at which you're exploring these forces, the strength changes. And there's a curious phenomenon that as you go to higher energies, the strength of those forces actually sort of approaches each other. So there is a hope that there's a grand unification of those forces, that at a very high energy, they actually are all just one force that at the lower energies manifests itself as the strong nuclear force, the weak nuclear force, and the electromagnetic force. So the question is getting at, obviously, as you go back in time, the universe gets hotter. So if you go back far enough in time, there will be an epoch in the universe where these forces got unified, the grand unification epoch. However, it's such a large energy scale that maybe it's very hard to learn anything about it. But do you think we'll make a breakthrough? And I think Daniela will let us know what his thoughts are.
Hi. So yeah, thank you. Thanks first of all, Sean, for summarizing what we mean with grand unification theories. Yeah, so the grand unification epoch, which is this epoch of the history of the universe where we expect this phenomena that Sean described to have happened if these theories are correct, are placed at a very early stage of the history of the universe. So we're talking about 10 to the minus 43, 10 to the minus 35 seconds after the Big Bang. And we just cannot probe directly such an early epoch. In fact, at the moment, the earliest epoch that we can actually directly detect is when we have the cosmic microwave background radiation. That is basically a blast of light that we see from all the directions in the universe that comes out because the light stops being all merged together with matter. It's like when you look at the sun, for example, you cannot see inside the sun because the light is continuously jumping from one particle inside the sun to another. So the surface of the sun is when this light basically manages to escape the network that is otherwise set by the matter. So the cosmic microwave background is essentially the same thing, but in reverse. So basically, we cannot see beyond this wall of light around 380,000 years after the Big Bang. Now, the fact that we cannot probe that epoch directly does not mean that we cannot know anything about it, but just wanted to make the point that what we need to do before this cosmic microwave background radiation is to sort of extrapolate our theoretical models based on the observations that we can observe and try to figure out what has happened before. So from the experimental point of view, which was, by the way, the scope of the question, some attempts have been made in the context of particle accelerators. For example, if you are like smashing particles so hard once against the other, for example, like in the LHC collider at CERN, you can try to sort of achieve the energies, to go closer to the energies that you expect could be there in the very early epoch in the universe and try to get a sense of how the universe should have looked then. So basically, we try to recreate that in a lab. But there's also another recent advancement which I think is pretty cool, and I've heard that together with Sean at an earlier conference that we organized together this year called the Multiverse from Home conference. And Dr. Alex Jenkins from the University of Cambridge gave a talk explaining that they are building some experiment. They have built, in fact, already an experimental apparatus where they use super cold gases to try and reproduce what we think might have happened in the very early universe. It's not exactly about the grand unification theory. They try to understand what has happened during inflation, which is a period of super fast acceleration in the very, very early epoch of the universe. So we're still talking very early universe. And I think that was really, really cool. Now, whether I think we will definitely make progress and in that way and understand what happened in the very early universe, that's very hard to say. But I think that those things are, these ideas of recreating the universe in a lab, to me, look very promising.
Cool, thank you. So Sanket, I think you wanted to have a follow-up?
Yes. So so a very quick follow-up to what Daniel already mentioned. So he mentions a very interesting approach beyond the CMB to probe the energy scales at the gut scale. But it's also worth mentioning that in the upcoming years we have also very promising gravitational wave uh, like detectors, for example, Einstein telescope and the LISA and so on, which can actually probe the energy scales much higher than the CMB. So it does give us a very good idea about what might have happened at those energy scales and so on. So that's I think like one of the most promising observational probe that we will have in the next 10-15 years.
Cool. Sergio, do you have a thought on that?
Yes, I wanted to kind of add up on what Daniel said. That is, of course, yeah, we cannot see what happened in the good scale. For example, we know that in order for the good scale to exist, we need, right now, well, one of the solutions was supersymmetry that hasn't really been found yet in the LHC, but it could be there maybe in the future. But not only that, but if you have some of these very strong theories, of theories of everything, it's not only in the lab, but like cosmologically, there is a lot of hints that we can take in the late universe. Like if this type of theories expect so many new particles to be around that, well, we are not seeing because maybe they don't interact very strongly with the standard model. But even if they don't interact strongly with the standard model, they can still interact strongly with gravity in a way. So one of those fields could be, for example, the quintessence that we mentioned before for the expansion of the universe. Or it could, for example, also you would expect, like if you have, I don't know, let's say that string theory is one of these solutions. That string theory is, well, one of these most crazy theories to explain all of this, and one of the solutions that one of the requisites it needs to solve this quantum mechanics general relativity disparity is basically to include more dimensions. And you have to compactify these dimensions. And long story short, when you compactify these dimensions, the main tell that you can see if there are dimensions being compactified is that it seems that gravity has been modified in uh, in ways that basically need new couplings to the standard model. So yeah, if we find modified gravity, or if we find quintessence, or if we find new many particles being coupled to the standard model very weakly, this could be hints that there is a theory of everything merging all the forces in a gut scale. Of course, it wouldn't be like direct evidence, but it would be a very nice hint of that.
Cool. Daniela, do you want to follow up?
Yeah, so thank you both for your comments. Yeah, so I was actually specifically focusing on direct probes. That's what I said, directly probing what happens before the CMB. But that is not to say, of course, that we cannot figure out what might have happened indirectly in some other ways. And yeah, surely also with late universe observations. But since Sanket was talking about also, yeah, future, what we could get in the future. I also heard a couple of years ago at a conference discussions of a much more longer term possibility of probing the very early universe directly, which would be instead of with light exploiting the signals from neutrinos, in the sense that you remember what I've said earlier about the cosmic microwave background being this blast of light that is the earliest light that we can observe in the universe. Actually, and that's because the light, as I said, at some point stops being all packed with matter. Something similar happens much earlier in the universe. I think now I don't remember exactly, but I think it's probably of the order of minutes after the Big Bang. But I might be wrong. Of neutrinos also escaping the net of all the other stuff that is there in the universe. So instead of having a cosmic microwave background, you would have some sort of cosmic early neutrino background or whatever. The problem is that it's very hard to measure that directly because the neutrinos can then, well, first of all, they're very elusive to observe, and also you get, neutrinos from the sun and from other sources around, so it's very hard to distinguish amongst them with experiments. So there are some of these proposals of like putting some observatory on the dark side of the moon or something for neutrinos, but I don't know. So that we're talking about something much more longer term and perhaps more science fiction at the moment. But I think it's also cool to brainstorm about the far future every now and then. Oh, thank you. Sanket said, oh, 1 second. You're right. 1 second. The cosmic neutrino background. Thank you. Yeah. Thanks.
Okay, let's see. Nico, I think you have a thought.
Yeah, just in general, probing very early universe. There are, I mean, first you need to, as they were talking about, define how early. But also CMB is not completely exhausted, right? There are we had at Cosmology from Home was it last year or 2 years ago? We had a plenary by my brain just stopped. Jens, right? Jens talked about other ways of extracting information from the CMB, and they are working pretty hard on trying to get funding for experiments of that type. Or 21 centimeter line. I don't know if somebody like Sean, we probably know
Was
more about it
spectral
than I do.
distortions, I think, is what you're
Spectral
referring to.
distortions of CMB, yes.
Spectral distortions are deviations from a blackbody spectrum. So the CMB is very, very close to a blackbody being the thing that something in thermal equilibrium will emit. So if you let something just sit for a while until it gets to a very, 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 very clear temperature, it'll give off light, and that light is called a blackbody. And the CMB kind of satisfied that. It was there, nothing external to it, obviously, because it was the whole universe. Well, not the CMB, but the thing that emitted the CMB, the hydrogen plasma, the early universe. And if there were deviations, they'll tell us very, very interesting things about the early universe. And so having a telescope experiment directly looking for spectral distortions, deviations from blackbodies would be very, very cool. Sanket, I think, had a question he wanted to.
Yeah, can I just for this is just for the general public, because we do mention black body a lot, but we never explain it completely. And I think the best way is like a very hot, dense body emits a light, and when you check the spectrum, it has a very specific curve. And for example, stars are like that, right? They're very compact, hot objects. So stars spectrum is actually a black body spectrum. And then this is one of the ways we figured out that the universe at some point had to be very small, very dense, because it's a almost perfect black body.
Okay, I'm going to show my ignorance about astrophysics again. I thought stars weren't close to a black body, but
They emit as a black body. The
okay.
spectrum. Yeah.
Okay. So Sankit's question, well, no, not Sankit's question, sorry. Sankit wishes to answer this question. Earlier this year, I heard a theory suggesting the universe was expanding at a changing rate. Has there been further developments on this, or is it all fairly speculative at this stage? And what are the implications of a variable rate of expansion? I want the person who asked that is in the Reddit AMA, and I want to give them points for the fact that I actually don't think I need to unpack that question. I think it was a very clear question. Sankit.
Yeah, so I did try to answer it on the Reddit itself, but it's a very nice and interesting and relevant question, related to the recent observations as well. So so what the person has been trying to, I think, ask is the nature of the evolving dark energy. So what they've asked is that is towards the lines of the expanding rate and the like whether it's constant or has it always been like varying or not. So what I tried to answer is that so the expansion rate, it depends on the what matter energy content you have in the universe. So for example, in the very early times, the universe was dominated by radiation, followed by matter domination, and during radiation and matter domination, the universe did expand, but in the decelerated way, and and as the universe expanded, the density is diluted, and eventually dark energy, which in the standard model we suppose that it is it's constant. Over the time, what happens is that because of the energy density is dilute for radiation and matter, dark energy dominates eventually. So my point was that in the entire history of our universe, the expansion rate has always been varying and not constant. So so according to the standard model, as I mentioned, that dark energy is supposed to have the constant density, but the recent results from the DESI, they do suggest that it might not be the case. It's possible that the dark energy density might be varying, and that would have very different implications on the future of our universe. So and yeah, if anyone else wants to add anything to the dark energy and its evolving nature, it would be great.
I believe Sergio has some thoughts.
Thanks, Sanket, for the nice explanation about that. So something I wanted to add is, again, going against almost the question, that is that it's true that this experiment DESI claimed to find that dark energy is changing with time, or there is some weird behavior with dark energy. And I would like to kind of try to explain at least what is so weird about what DESI found. So basically, say that we want a change in dark energy. And let's say that this change in dark energy, there is some model that makes sense with the formalism that we currently have with quantum field theory or cosmology. Everything we know about, literally, like in a way, about free fields in the universe. It really seems that that when you try to build up some model to explain how this is finding the universe to explain, is basically impossible. You will be creating energy from nothing in a way. So it's just that was kind of like a big hit to the science community. However, that is not the complete story. The reason why it seems that it's impossible for dark energy to be varying in that way is because maybe it's not dark energy what is varying in that way. Why is that? Because in a way, what they have found is not really an observation on dark energy itself. What they are measuring is something else, is how much matter there is, like the fraction of dark matter today in the universe, or total matter, or how far away are the supernovae that they are measuring to get this data. So because they are finding some tension with Planck, that is this other big experiment to measure the expansion of the universe, basically they need to kind of tweak some things today so that everything looks perfect in a way. And you can put everything and all experiments are in agreement with each other. But because we don't know what is making this kind of change to the universe so that all different observations are satisfied, someone has to take the blame. So that's the only reason. Who can take the blame to explain everything? Well, it cannot be the standard model. Why? Because we really know what the standard model has been doing since the beginning of the universe, or since the CMB, cosmic microwave background. But so we are going to put it into a dark sector. Can it be dark matter? Well, dark matter is kind of difficult because we also know a lot of dark matter because of it has been kind of creating the galaxies and giving shape to everything, all the structure that we see today. So the only one that can take the blame right now is dark energy. So that's why we say that dark energy. But there is another possibility that they also mention in the papers. That is the other big thing that we don't know a lot about in the standard model, that is neutrinos. So it could be that neutrinos are changing their mass with time, or maybe that dark energy is changing its kind of parameters with time. But it could also be that there is some type of interaction between different sectors in the universe. And that's kind of the last thing that I wanted to say, that if you remember, like before I said that it's a free field cannot explain how this is happening. The obvious also answer is that maybe this is not a free field, that there is energy going from one field to another. And because we are not taking into account this change of energy going from one sector to another, we think that like we have to make up for that change with only one field, and it's impossible to explain all of that with only one field. So in reality is that there are two fields doing crazy stuff. So yeah, we don't know if actually there is dark energy doing crazy stuff. It's just we see that there are two experiments not being in agreement with each other, and when you want to explain that, someone has to take the blame, and you can put that in different sectors.
Awesome. Thanks, Sergio. That was an awesome answer. I really like Tale of Benji's question in the YouTube stream, so I'm going to bring it up and maybe tackle it myself. But I'm not a complete expert on this myself, so maybe others in the room can also tackle it. But the question is, how is the CMB power spectrum actually obtained? I never quite understood the practicalities of this, and the papers on it seem very esoteric. The reason I like this question is that, yeah, like especially in streams like this, but whenever cosmologists are explaining it, they say, we measure the CMB. And okay, what does that even mean? How are we actually doing this? So here's my attempt at an answer. So yeah, the cosmic microwave background is this light that's been traveling from the early universe. If you go back in time, the universe gets much, much hotter, and eventually neutral hydrogen is no longer stable. The electrons can be torn off. So if you go back in time there, you have an opaque universe, and then universe cools, hydrogen forms, and some light starts forming. So that's what the CMB is. How do we measure it? Well, each telescope that's pointing at the sky will measure light in different frequencies. It essentially just measures the intensity of the light in these different frequencies. Now, there's lots of stuff emitting light at those frequencies that is and isn't the cosmic microwave background. So what the first thing they have to do is work out what actually is the cosmic microwave background inside of the signal. And that's why they have to measure at multiple frequencies. So other things that are emitting light will change with frequency in a different way. I guess we've already talked about this black body a few times. It has a very specific way in which the intensity changes as the frequency changes. So you reweight the kind of combination of these different frequencies, the intensities as frequencies, to cancel out the non-CMB and get the CMB. So after that, you have essentially a map of the CMB on the sky. You have to mask out parts of that map where the galaxy is and things like that. I mean, you certainly have to mask out stars because you literally can't see behind the stars. Your telescope is just completely, the star is so bright that you don't see that area. But you have to mask out the galaxy as well because it's just too hard to extract the CMB from behind the galaxy. But you essentially have a map on the sky. That's what the CMB was like at that point. And then to get from that to a power spectrum, I guess I would have to try and unpack what a power spectrum is, which I think I might not have the mental alertness to do right now. But the power spectrum is essentially saying how different parts of the sky are correlated with each other. That if the temperature is slightly higher in one direction, is it going to be slightly higher in another direction? And there's a way of quantifying how the temperature is related in different directions on the sky. But that's essentially extracted from this map. You've looked at the sky in multiple frequencies all over the sky, and then you've reweighted the amplitude with these frequencies to get a best estimate of that was what the cosmic microwave background was in that direction. If, Tale of Benji, your question is, how do the telescopes actually work? I am certainly the wrong person to be answering that question. They point and they collect light, and then some detector goes click, would be my very technical answer to that. Does anyone else want to add anything to that? How do the telescopes actually work, if anyone knows that?
Yes, sure. Like, may I have a go at it?
Yeah.
Well, depends on what you're looking at, right? You first need to understand if you're looking at light, but light has, if you remember, light itself, it's an electromagnetic wave, so you can look at different frequencies of the light, right? So in terms of CMB, what they do is they have these basically radio antenna. So it's like radio part or microwave part. This is the frequencies or the energies or the and now I forgot how to say the wavelength of the light that you're looking at, right? Optical telescopes, right? They only look at the optical, what basically we can see with our eyes, and then there's other types of telescopes like a gamma telescope. The famous one is Fermi. It's finished. But it has a lot of data, or X-ray, and so on. So that's how that they basically are looking at the sky in radio or microwave frequencies in order to study that. And then it's not just there's frequencies, for example, the way if you're looking at optical, if you think about optical telescopes, you can also look at the spectra, or you can look at just the image itself. So that way we have different types of experiments that are basically just doing the spectra of the objects that you're looking at. That's called the spectroscopic survey. And if you're looking at the images, literal images of the galaxies, like Rubin is doing, that's the photometric, like the imaging survey. So you're extracting the data in different ways, because if it's the imaging survey, you can actually look at not just the positions of the objects, but also their shape, which is a very important probe in cosmology. And in CMB, what Sean was talking about, they're looking at basically radio, and then they play around with that signal, right? The data comes in, and then you have to calibrate it for the sources that are nuisance sources to you, right? Locally here, what is really what we call radio loud, that means some objects that are really emitting in radio is, for example, the sun. Jupiter, for example, is also a very big radio source. And then in some galactic plane, depends on where you're looking at, or some black holes and AGNs, called active galactic nuclei. They're also very loud in radio. So I hope I gave you a little bit of idea. The neutrino experiments work differently. We have a fantastic telescopes, experiments that are looking at neutrinos, and neutrinos are very tricky to deal with because they don't want to interact with anything. So you need a very large volume in order to study it. And what is the volume? You have to force not force. You can't force anything, but like you have to have a very big, we call it active volume of the detector. And what they do, they have very cool experiments in the Antarctica, like in the South Pole, that are using basically the whole Earth in a way as the active volume. They have drilled very deep, 3 kilometers deep wires, and I think they have hundreds of these wires into the ice. And then they are basically trying to detect, or they are detecting neutrinos when they pass through 3 kilometers of ice sheet and through these wires, or the big Super K and the Dune experiment now that's coming, that are basically filled with some liquid, where they are hoping to detect neutrinos interacting. So then the signal, of course, you have to wire the experiment, put the cables on, have some nice computers, and then a lot of smart people to process that data. That's how it works, basically.
Cool. Thanks, Nico. We wanted to do a kind of like academic life-ish question here. I think I'm next. Sorry. I think I'm gonna try and frame it the following way. What is one piece of advice you might have given your past self, if you could go and give your past self advice at any point of your past self, and only one piece of advice is allowed? What would it be? Because I think that there might be some people watching this now or in the future who are at some point of an academic path, and wouldn't mind some advice. Does anybody want to tackle that first?
I think this might have been the most difficult question so far.
Yeah, probably. Well, Sergio wants to tackle the difficult questions, so off you go.
I would take the difficult, like for me, it's very easy. And I would go back probably to my first year of PhD and tell myself that working more hours doesn't mean getting more done. That's the basically thing that I remember that well, when you start your PhD, you think that you need to get results within the first week or 2 weeks for the project that they have given you. But now suddenly you go from having weekly tasks and exams to having projects that last for, well, maybe months if you are lucky, or maybe years if you have a standard PhD. So yeah, it's important to know that now you have to take care of your health, both mentally and physically, have your head a little bit more, well, rested, so that when you work, you can actually get things done. And sometimes if you're tired, then it's good to just leave it for the day and start again tomorrow.
Cool, thanks. I kind of wanted to jump on one of the things you said there about how, yeah, as an undergraduate, I think I remember one of my undergraduate lecturers talking about how you're literally like Nobel Prize per week, and you're just rapidly learning new stuff. And then suddenly when you're actually doing original research, you have to come to terms with just how slow everything is. And like even someone like Einstein, who's like famous as being very successful as a scientist, he lived for 50 odd years. He was a researcher for 30 odd years, and there's like 4 or 5 famous things he did. I mean, okay, that's amazing, but that's over 30 years. So even he was like quite slow paced compared to your average undergraduate who's earning a new Nobel Prize every week. And further piggybacking on that, there's something that I think every researcher has to eventually come to terms with or explode through imposter syndrome, which is that everything you know how to do feels trivial to you and not that difficult, and therefore like not that valuable, and everything you don't know how to do seems very difficult. So you're constantly, no matter how good you are, facing the fact that everyone else seems to be way more competent than you because they're good at the things that you're not good at. But the things you're good at only seem easy because you've spent lots of time working on them and thinking about them and learning them. To everyone else, those things still seem difficult. And maybe a good framing thing is to always think back 3 months or 6 months or 9 months. Would 9 months ago me have thought this was really difficult? Probably yes. So the fact that you spent 9 months banging your head back against it and learning stuff, everyone else is still stuck in the 9 months ago you. So it's very easy to get into that imposter syndrome situation where all the difficult stuff and good stuff that just feels trivial, because to you maybe it is now because you've learned it, but the fact that it's trivial should give you confidence, not make you think that it's actually low value. I think do you have a follow-up to that, Sergio?
Yeah, can I follow up? Yeah,
cool.
it's just I love that because it's something that I think of it like maybe once a week, the fact that everything is impossible until you understand it, that becomes trivial. But like I will go one thing farther ahead, that is when you're doing research, the stable point in research is being frustrated on a problem. In the moment in which you solve that problem, you will find a new problem for which you will be frustrated and will be impossible again. So if you are in that situation where you are struggling with being frustrated because you can solve a problem, instead of working to put in all the hours to solve that problem as soon as possible so that it's not frustrating you anymore, will not work because a new problem will arrive. So your time will also go into just being comfortable with being stuck on a problem, enjoying being stuck on a problem, and just that's how academia works. That's you're solving the puzzle slowly, but that's how research feels like.
Cool. I think next in the queue is Priyal.
First of all, amazing advices, both of you, Sean and Sergio. Like really, imposter syndrome, especially, it's like it's an everyday struggle, especially when you're in the masters. It's like you just have 2 years. For bachelor's, you have 3 to 4 years, but suddenly in master, it's like 1.5 year for studying, and you're jumping to your thesis, and it's like constant burnout, and you're saying goodbye to a lot of friends, especially when you're international, and it's like everything tolls on you. But the one advice that at this point of my career I could give someone is when we are in our bachelor's and masters, we try to we try to drop all of our passions and a lot of activities that we used to do as kids or in high school, even until our masters, just because we think that as a physicist we just have to do physics, and it affects our work a lot of times, and we forget to realize is that a lot of our other passions can contribute so much to our activities of physics and our research in every day, because it's important, as you said, that the timeline of research is quite long. So it's important to keep ourselves fresh and not drag ourselves towards a burnout. And one of the things that we can do, for example, is joining a bit more of science communication a bit early on, because personally, I've found this really, really helpful. The community where you're more social, and I will give you a very basic example. So I used to be active on Twitter some years ago, and there was Nico and other physicists there. And I cannot tell you how much it motivated me to come outside of India and apply for masters, because like, oh, they're also like super cool. They're researchers, and they're not like working robots who just talk about physics all day, and it can be in so much fun way. So yeah.
Cool. Thanks, Priyal. I guess Nico is next, I think. Yep.
Yeah, so my advice to myself, well, in any stage of my life before January this year, when I moved here and started a new job, would be, believe it or not, eating well, sleeping well, and doing some exercise actually is good for you. I know that I needed to get a PhD in physics to understand that, but actually it's true. So yeah, maybe it's okay to work hard if you like it. That's completely, I mean, everyone works differently. It's just that save some time to actually get some sleep and eat well and move. I don't know, get a bicycle or something. Yeah.
Okay, I am about to start my career as a self-help expert with the surge technique. Okay, this is something I use in my own brain, and it is sleep, exercise, reflection. Just do it. But that's the order of hierarchy. If you're not sleeping well, there's no point doing anything else. And if you're not sleeping and doing exercise, there's no point doing anything else. And if you're not sleeping, exercising, and then reflecting and just sort of evaluating peacefully what's going on, there's no point doing anything else. But once you've slept well, exercised, and reflected well, you can just do it. That's the surge technique. Trademark.
May I just jump in on the reflection? Depends on what you mean by reflection. Self-reflection every day, or that I would never recommend. You are allowed one reflection per month, because that can lead to some depression, right? Don't just do it, and then sometimes, of course, you should self-reflect. But
Yeah,
assessing maybe the situation.
That might be a person-specific advice. For me, reflection always helps me out, but I think I'm a relatively positive thinker, and it settles my mind.
If you're a positive, that's fine. But if your tendency is to go into the dark spot, I would highly
yeah, for
advise
me,
you against
reflection is like
self-reflection.
cleaning my room. Like it before I do reflection, I have 1,000 things in my brain that I'm trying to keep occupied, and that causes me a little bit of stress. But then when I reflect, it's like everything goes in its proper space, and then I'm calm afterwards. But I can totally get that if reflection leads someone down other paths, maybe you should stick to sedging rather than surging. I'm not sure. I think my career as a self-help expert just imploded. Swagger, you're next. Oh, sorry, Swagger, you're not next. Sankit is next.
Yes, just a very quick follow-up on that. So yeah, I mean, yeah, it's so the stuff that we do is it's actually really hard, right? I mean, we are not evolved to do science at all. I mean, we are not supposed to do all these things that we do. So it's okay to just step back a little, just think about like a larger picture and so on. So I mean, just go for a walk, or just so like for example, for me, if I am stuck solving a problem, or maybe or for example, I was also applying for the PhD positions, and it was not easy every day applying for a new position and getting rejected, and it's like staying at home for 1.5 years, not doing any other job. So it's so at times it does get a toll on you. since you also have to do your research as well, you have to like prepare for exams as well and apply as well. So it's not easy. So I mean, what I would do, I mean, what I've like realized is that, I mean, you can just go for a walk. Just what I would do is I have an 8-year-old niece. So I would just call her and just talk any random things with her for half an hour. For I mean, and it's just nice. I mean, just all these random things which are important to do. I mean, it's just and it's okay to feel stuck, but yeah, it's just how it is.
Cool. Swagat, we'll go to you next, but I want everyone to start thinking about Tale of Benji's question. Have you ever felt that you wanted to take a break and do something else for a while? Asking this as a seniors master student who is soon entering the space between unemployed and PhD. So yeah, Swagat, and then we can come back to that because I think that's a good question. Tale of Benji.
Thanks, Sean. Yeah, sorry to change the topic because I thought I'll cover a slightly different angle also. So what advice I would give to my younger self? I would say that this is a technical part aspect of physics answer. I would say learn statistics very, very well. It is very important as an empirical scientist to understand what statistics is. So that I will highly recommend.
Yeah, ultra
I could
practical.
not
I like
agree
it.
more.
Yeah,
Yes.
yeah. We're all like, mental health, this and that. And Swagat, yeah, learn statistics. That's that. Yeah. Right. So what was it? Tale of Benji's question. Have you ever felt that you wanted to take a break and do something else for a while? Yeah. Does anyone want to dive into that? Sergio.
I'll go again first. Yes, maybe once a week, once every 2 weeks. No, but there's always this meme in a way, right? That all physicists doing, or everyone doing a PhD or doing academia, you have like a plan B. Either it can be open at a bakery. In my case, it's opening a bookshop, and that's always in my mind. So yeah, I mean, but that is I think that's I'm joking with this, but it's very common. Like it's very easy to burn out, and we put a lot of pressure on ourselves because we are working in our passion. So it's very weird to feel burned out on your passion because it's the thing that should keep you going. But in a way, the good thing about physics always is that you can do many, many things outside academia. And I'm sure that you have to keep in mind that right now you love physics because physics is super fun, of course. But basically, you know the problems that you are working with, and they are very interesting, and you're part of those problems too. But something that I always keep in mind, always, is that given that I don't have a secure job in my future, it's very probable, like all the probabilities are that probably I will not end up inside academia because it's very hard to get a permanent position. But there are many things that, although you're not doing, maybe you're not working on the universe exactly or on cosmology or in physics, but there are other jobs that I'm sure that once you start doing them and learning about the different things inside those jobs, you will find beauty in the problems that you are solving. And maybe doing, I don't know, let's say banking, yeah, although you will be selling your soul to the evil, but let's say that you're trying to kind of predict or like how some data is evolving, and it can be for good causes or bad causes, call it as you want, or it could be in a company that is trying to kind of develop new software for something that is very positive. I'm sure that it doesn't matter where you end up, you will find a problem that you will need to solve, and you will end up falling in love with that problem. So yeah, we normally, I think, that romanticize physics too much. There is life outside physics. That's the most important thing.
Thank you. Andrea.
Yeah, thank you. And thanks, Tale of Benji, because this question actually had me came up with an advice that I would give my past self, which is that liminal space that you mentioned between unemployment and PhD or whatever and an academic position is something that we tend to stay away from. But looking back to my past experience is something that I should have enjoyed more. It's one of those few times where you can actually take the steering wheel of your life and potentially try to explore any possible route ahead. And I think this is something that we should give more value to.
Cool. Nico?
Well, the answer is no. I do not at this point want to do anything else. And for a very long time, I really just want to do this. I was up to here, very lucky to stay in academia. I don't know what's going to happen tomorrow, but this ties into my previous answer about self-reflection. I do not think about problems before they happen. So once I'm faced, if I'm ever faced with the problem of trying to find another job in somewhere, I mean, I have a PhD in physics, I will find a job. And it doesn't have to be a fancy job. I can also, clean the houses. I don't care. But as long as I'm having fun and I'm able to stay in academia, I would not change the job, except maybe to be an FBI agent, but I don't think that's going to happen.
You heard it here first, FBI agent Nico. Priyal.
Well, so as I was saying before in the last question, that we have to keep exploring our other sides of our passions other than physics also. And I'm sure everyone has a second passion, definitely. And my mentor at Supernova Foundation, she has always taught me this thing, that do not live your life under a single stamp. And it motivated me to explore my creative side, that is art. So I would really like to be a designer, like an all-rounder designer, a fashion designer, a jewelry designer, and also do interior designing, whatever I can do. So yeah.
Cool. Should we get back to some cosmology? Does anyone have a cosmology question that has been asked in the stream or in the Reddit AMA, or that they just think is an awesome question to bring up themselves and answer now?
Yes, may I? It ties
Absolutely.
in with something that Swagat mentioned, and then there was asked on Reddit, and I can't find it now. I'm sorry, I'm scrolling. But it was a question about statistics. And well, to us is very, very clear that usually the way we do cosmology is more like a Bayesian approach. You can do the other thing as well, or try to. But maybe Swagat, do you want to start answering that? Basically, what is? I mean, I can give a brief overview of Bayesian versus frequentist, but how maybe the question should be for all of us: how does statistics go into your work? How do you tie it? Because it is everywhere. Maybe that would be interesting to people. So there's two main approaches in statistics. One is called the frequentist method, and the other one is Bayesian. And the main difference is how you treat how you approach the whole problem. So and the difference in the two is basically the frequentist you can maybe I can give us explanation in a very, very different way. In particle physics, they usually do frequentist method of dealing with their data, or the frequentist approach, because they can repeat the experiment first and foremost, and what they measure is a signal. So, for example, single event. Whereas here in cosmology, what we observe is more like a distribution. So we don't have a single source signal. And another difficulty is that we have one universe. So we can't repeat the experiment. And that's in that sense the way that particle physicists can. So different nature of the problem requires different approach. And this is the main idea. And it's very easy to look up the Bayesian, for example, based formula, or the frequentist method. There's a lot of fantastic resources online, especially on YouTube. There's this stats guy I would highly recommend, because he has very good videos and stats. So I think you should start that. But this is the idea of the problem, or the approaches of statistics, and how we basically the whole cosmology, some sort of statistics. At some point, Sean mentioned the power spectrum. And the power spectrum is something that we all deal with in physics, one way or another. So, for example, we do the way I do physics for example, with LSST, this Rubin Observatory. We can look at all of the galaxies that we see in the images, and try to find where they're positioned in the universe, and also look at their shapes. And then we call it correlating all the pairs, possible pairs of galaxies, and you can also do it statistically. Basically, what you can ask yourself, if I have a galaxy here, what is the probability I'm going to find a galaxy there? And using this sort of statistics and then doing some fancy mathematical thing where we do something called Fourier transform of these correlations, that's the power spectrum. But maybe now I'm using too many fancy words. But basically, it is a lot of statistics and probability. So all of the results that we're going to present is actually giving you some sort of probability. And this is how science usually and should report. It says, okay, this is the most probable answer with the error. And I'm so much confident about it. I'm 95% confident that this is the answer. So I hope I managed to explain it, because I don't want to use a lot of fancy words while explaining the unknown. So maybe Sean, you have a tick, so please go ahead.
Yeah, I think I have a few thoughts to sort of add maybe. I find that the discussion about Bayesian versus frequentism conflates two things quite often. One is Bayesian versus frequentist inference, and one is like the fundamental theories of probability. And these things are kind of related. There's frequentist interpretation of probability, there's a Bayesian interpretation of probability, and there's frequentist inference and Bayesian inference. If I can try and like make a broad brush explanation of these things, the frequentist interpretation of probability is that you can only talk about probabilities in terms of relative frequencies, that like something has a bigger probability if it's happening more often than something that has a smaller probability. And as Nico said, in a particle physics experiment, you're talking about like count rates. How many times did this energy channel go click when I did a collision, and then I measured how much energy came off in that direction. You can just keep doing it and doing it and doing it and doing it and get a relative frequency that, this click happened this many times, this click happened that many times. And in some parts of cosmology, you can do that, but we do have the problem that we can't just run the universe millions and millions of times and get a nice frequentist distribution. So on the Bayesian side, you're instead just saying degrees of belief, like given on the kind of fundamental side of probability, given all of the things I have learned about this thing, what is my posterior, what is my final belief that this model is the correct model of the universe? On the inference side, I guess if I had to do a broad brush explanation, it would be that the frequentist question that's normally being asked is, what is the probability of the data given the model? So I have some model, and then I made some observation, and I'm saying, what is the probability that this observation could have happened if the model was true? And then the Bayesian inference side is essentially asking, what is the probability that the model is true given the data? So I've measured all of this data. What is the probability that this model is the correct model? And those sort of sound like the same question, but they are subtly different. And if I was to give my kind of opinionated answer now, probability of data given model is the wrong question. It's not actually what you want to know. You want to know, is this model of the universe the correct model of the universe? Is this the right dark matter model? Is dark energy evolving? These are model questions. Is this the right model? And probability of data given the model is like, how likely was this? It's hard to immediately translate that if you get a small number into, is it the right model or not? Okay, the probability of the data might be small, but does that mean the model's not correct? So the problems with these two sides, in my mind, again, this is an opinion, is that on the, I guess I've already expressed the problem on the frequentist side. What is the probability of the data given the model? If it's not the question you're certain you want to ask. To me, the problem on the Bayesian side is that I need a kind of alternative model. I can only be comparing models. I can't just do a fundamental, is this model working? I've looked at the data, is it working? I don't have an alternative model. I just want to know, is Lambda CDM doing a good job? And it's not possible to answer that question purely within Bayesian statistics. You have to compare it to an alternative model, the kind of goodness of fit question. So I do like, I think Bayesian questions are normally asking the right question, except for that one time when I just want to say, is the data fitting? And then you want to ask a frequentist question of, is the data fitting the model? And then if it isn't fitting the model, it's not saying you need to throw that model away. It's just saying, hey, there's a lampshade pointing in this direction. Go have a look. You might find alternative models that fit the data better. But dyed-in-the-wool hardcore Bayesians will grump at people who ask that goodness of fit question. And I think that they're missing a chance to like turn that lampshade on and then ask the question that they actually want to answer. Nico, you have a tick.
Yeah, I was trying to answer to people at the same time. I think the channel for the stats is called Stats Watch or Stats with Josh Starmer, Stats Quest. it has 1.5 million subscribers. I really enjoy the channel. It's very nicely explaining things. What I wanted to say about the stats here, what Sean was saying, and I want to bring up that what bothers me in this whole Bayesian versus frequentist is no one's fighting with each other. There's no like, oh, who's better, who's right. It's just that, for example, you need to dig a hole. I don't think you're going to start with a hammer, right? So you're going to get a, I don't know, shovel or something, spade, right? If you need to dig a hole. So it's just a different problem requires different approach. And there was another point I wanted to make, and now I can't honestly remember what I wanted to say. It was something very smart. I can promise you. It is. Oh yeah, the Bayesian approach is basically. I think I heard it somewhere. I can't remember to give proper credits, but it's like, oh, everyday life is very Bayesian. For example, cooking is a very Bayesian process because of the prior. So, for example, you think you have some idea if your soup is salty or not, but you have to taste it and then you correct your prior. Oh, this needs more salt, so you add more salt. So it somehow works like that, and this is how we do cosmology, right? We have some prior knowledge, hopefully. Then we do our analysis, and then we have to correct our beliefs based on some other knowledge. So it's pretty cool.
So I don't see anyone with a hand to ask a new question, and we're coming up on the 2-hour mark. So I think I'm going to have one last question for us to wrap up. And I'm trying to scroll through our internal Zoom chat here to find the exact wording that I think Priyal was using based on someone who'd asked in Reddit, but it was something along the lines of, what's your favorite part of cosmology? So if I've paraphrased it successfully enough, we can just do that. But if Priyal, you want to clarify that in some way, if I haven't got it exactly right.
I'm also trying to look for that question myself.
I think that's probably close enough. What is our favorite?
Oh yeah, the question
about
is same.
cosmology?
The question is exactly same. I was just looking for the credit. It's asked by Fluffy Haru.
Okay.
They're just asking about favorite parts of cosmology. So yeah.
Yeah. So does someone want to jump into that?
I mean, I can start maybe since I'm already on. So for me, the most favorite part of cosmology, the one which led me to enter this realm, is how we can understand what happened at a particular time through all these calculations, which is kind of why we started studying cosmology, to understand the timeline of the universe. It's a very basic thing, but this is what drives me, because it can be these things can define a lot of things like arrow of time, and we can talk about quantum gravity realms in some way. We can also talk about quantum cosmology and a lot about primordial black holes. So yeah, some things that I will be working on soon. So yeah, I'm a bit biased towards that side.
No, I mean, it's as biased a question as this is the one question where we can be as biased as we want to be. No blinding. I'm not sure how you would blind this question. Does someone else want to tackle the question? Andrea?
Not sure I have a favorite. I mean, I can boil it down to a favorite part, but I think like the fascination that I get from it is the fact that we are able to get like a decently successful, well, actually very successful under some points of view, description of the whole universe we can observe throughout almost the entire lifetime of the universe. And like this is already giving goosebumps, basically. It would have been unthinkable at the, say, beginning of the 20th century. Unthinkable. And this is something that fascinates me. And like when I think about it, I feel really grateful that I can work on something that goes in this direction.
Cool. Swagat?
Hi, yes. So I would like to give my personal answer, and there are 3 answers of 3 different hierarchies, priorities. The first priority answer is very scientific, that I really want to know what our universe is, how was it created, how big it is, what is its fate. So that's the major reason why I'm in cosmology. Now I'll give 2 more answers which are slightly technical. The second answer is cosmology is a topic where almost all physics is applied. So as an undergrad student, I studied many different branches of physics as well as mathematics and stuff. And cosmology is a field where I get to apply them all, so that I like. The third thing is, which I would usually answer if another uh, theoretical physicist asked me, the answer is to discover new laws of nature, which we probably cannot do by just building bigger and bigger detectors, because we'll run out of our technology of building a bigger detector. While in cosmology, in the universe, our early universe had a lot of energy, and by carefully looking at the universe, there will be signatures and we can find out fundamental laws of nature. So these three answers for me.
Lost track of where my cursor was. To unmute myself, Sergio, I think you might be next.
I don't know if Nico was first, but I'll go. For me, what I think that it has been pretty clear in all my interventions, but for me, it's the expansion of the universe. It's just, I think that I started like learning cosmology just from the expansion of the universe, and it's the thing that I still think of and binds my, like, it just, for me, it's crazy. The fact that distances can grow between galaxies, and it's something that we just accept. I think that we just give it too much for granted now that we know about that fact, but what the heck? How is possible that distances are growing and the universe is expanding and we can understand it? And if I can add one top thing on this expansion of the universe, is just the coincidence problem is called. That is the fact that we know that the universe is expanding with a cosmological constant or something close to a cosmological constant. If for some reason life in Earth or in a different planet would have happened a little bit earlier, then the cosmological constant will not be dominated, so we wouldn't know that the universe is so interesting that it could expand, at an accelerated rate. And maybe if we had waited a little bit more to exist, maybe the universe would be so empty because the expansion of the universe would have dominated, that maybe we wouldn't be interested in cosmology in a starting point, because there wouldn't be stars to look at almost. So yeah, that for me is just super cool.
Okay, let's go to Sanket and then Nico.
Yeah, like one of the points that I wanted to mention was already mentioned by Swagat, that it's a very cool branch of science where we get to learn all kinds of physics. We need particle physics, we need a relativity, all kinds of cool physics that we can learn. And the second thing is that we can understand and we can say with absolute confidence that that what the state of our entire universe was when it was very young, and it was about 1 second old. And that's absolutely fascinating that we can actually do it. And uh, just by sitting at home, we are able to actually construct the theories that what the universe might have been when it was a fraction, like a billionth of a billionth of a billionth of a billionth second old, and so on. So I mean, it's absolutely fascinating that we are able to do it. And with upcoming observations that we'll have, we'll be able to say it with even better and more precision. So it's absolutely fascinating, and it's a really a brilliant time to be doing cosmology. Yeah.
Cool. Nico, do you want to wrap up the stream with your favorite bit of cosmology?
Well, there's two facets to it. First is not like, personal favorite, but I have to say that there is great joy, and I think that all of us feel very humbled by the fact that we can learn from each other, and there's like a lot of smart people out there who are super friendly, and it's just the atmosphere of working in an astronomy or cosmology for me so far has been nothing but great, and I just like love everyone. So these people want to actually, like just interacting with them in any capacity, learning is fantastic. Another thing that is super rewarding, what I find, and this is like, I don't know, my ego, but it is how I feel when you see somebody using your work, right? It's like, oh, I love your IA guide, or I love your, the code that you wrote. That was super helpful for me. I start crying because, somebody thinks your work is so cool that they get to use it. Regarding the science part, I personally am super fascinated by the clever ways of studying something. So you have to come up with a way of, how you extract the information, right? So if you're doing, I don't know, cosmic shear, or you're doing this tiny little effect of gravitational lensing that's very weak, and then you can extract basically, oh, universe consists of this much dark matter, this much dark energy, and so on, just by looking and having a lot of smart ways of processing that data. It is mind-blowing to me. And then later on combining the data sets, but just coming up with ways of using something as a observable, absolutely fantastic.
Yeah, I sometimes describe cosmology as like a detective story, right? Like, because as we were talking about in the frequentist versus Bayesian kind of comparison, that we can't just redo an experiment. We're very much like detectives who've just been thrown into a crime scene, the crime scene being the Big Bang, and like, you have been, we can't say, if only we could gradually increase the mass of various different supernovae and have different amounts of metals in them and different amounts of this and that, and their environment's different, and then just see what happens. We only get given what we get given by the universe, and we have to be clever and clever and clever and clever at trying to extract subtle pieces from that. And especially with something like the cosmic microwave background, where we're measuring, the polarization of the cosmic microwave background and how that correlates with the temperature and stuff. It's crazy how good at detectives we've become over the decades and decades as people to extract cosmological information. I am going to, I was making myself go last because I thought I'd think of something that was actually my favorite thing in cosmology, and I didn't manage to, but I'm going to just say something I think is really cool that people may not be all that aware of, which is tabletop experiments that might detect things like dark energy or dark matter. I think they're my favorite in the sense that if they turned out to be correct, it would be absolutely amazing, because you could just be studying dark matter in a lab. Thousands of labs all over the world could start doing it if it actually got detected. But there's, to give an example of a type of physics that might get detected in a lab, there's these models that are called screened models, where because of the way the physics works, which definitely you don't have time to go into detail, the force that you would experience from something like dark energy or dark matter might change with the density. And so the idea is that if you can create in a lab like a big enough vacuum, for example, that is far enough away from its shell, you might get a fifth force, an additional force that kind of creeps in. And yeah, people are looking for this in very, very well maintained and kind of $1 million labs around the world, instead of like a Large Hadron Collider or a telescope, which is hundreds of millions, if not billions of dollars. So $1 million is still a lot of money, but it's more feasible than billions of dollars. So that would be my favorite thing. If something like that got discovered in a lab somewhere, I think I would just explode with joy. With that, can we wrap up and maybe see you in a future
Yeah, maybe
stream?
put a gallery view so we can all just wave at the
Good point.
end.
Good point.
You're welcome.
We lost Daniela at one point because he went to bed because it's past midnight where he is, but the rest of us are still here to say thank you for coming and farewell.
Bye.
Okay, I ended the stream.